Today we'll start vector field theory or vector calculus, which, as all of you know, is very critical in understanding electromagnetic field theory. Most of the discussion will be in the Cartesian coordinate system. Once in a way we'll briefly enter into spherical and cylindrical coordinate systems. I would like to give a small briefing about the basic vector algebra that is required before we embark upon the calculus aspects. Basically, in vector field theory, we have vector differentiation and two, vector integration. Most of the things that we encounter here will depend upon the sound knowledge of vector algebra. So I would like to quickly take you on a small tour on how to remember the fundamentals of vector algebra and then connect it to calculus. For example, we define three-dimensional vectors a cap as a1i plus a2j plus a3k, b cap or b bar is equal to b1i plus b2j plus b3k. Now I, j and k are unit vectors along the x, y and z directions. a1, a2, a3 are the components of the vector along the x, y and z directions. Same is the case of the vector b. So it all starts with these two vectors and then they can be combined in variety of ways. For example, we can have the magnitude of A defined as square root of a1 square plus a2 square plus a3 square. This is nothing but the length of the vector. The third is the unit vector a cap. The unit vector of a cap is nothing but the vector a itself, but whose length is adjusted to 1 unit. Obviously, there is no change in the direction. So if you divide the vector a by its own magnitude, then that denotes the unit vector. Obviously, when you take a cap into a cap, you will get magnitude of a whole squared. One can easily verify that, but this can be a very useful but small result. Now we will then see how these vectors can be combined, a and b. We can add, subtract and multiply. So let us see that in the next slide. The dot product is given by a dot b is equal to the magnitude of a into the magnitude of b into cos theta, where we have the two vectors a and b including an angle theta. So this formula is useful in varieties of ways. For example, it can also be used to calculate the angle between the two vectors, provided you know the left hand side. And for Cartesian vectors, a dot b is nothing but a1 b1 plus a2 b2 plus a3 b3. This formula, as we discussed, can be used to find out the angle between the vectors. Of course, when we come to cross products, there is another way by which we can find the angle. But however, this is very, very convenient. A and B are called orthogonal vectors if theta is equal to 90 degrees. If you use this in this formula, we get the condition A dot B is equal to 0. Orthogonal vectors play a very important role in the vector algebra and ultimately in the calculus of vectors. Now let us see what is the cross product of two vectors. The cross product of two vectors A and B is given by the magnitude of A into the magnitude of B sin theta multiplied with n cap, where n cap is a unit vector perpendicular to the plane containing A and B. So this also provides us with an alternative to find out the angle between the vectors. So if you want to find the angle between the vectors, you can use the formula magnitude of A cross B divided by the magnitude of A into the magnitude of B. And A cross B itself for Cartesian vectors can be computed through a determinant ijk a1, a2, a3, b1, b2, b3. Obviously, when A and B become parallel vectors, then these two rows become parallel and therefore the determinant will vanish. So A cross B will be 0 whenever A and B are parallel vectors. Otherwise, you always get an output. So let us now go to triple products. Vector triple products are again very, very important because some of the vector calculus based identities involve triple products. So let us first define the vector triple products in which we have a notation box ABC, which is nothing but A dot B cross C. As you can easily see, B cross C produces a vector and its dot product with A produces ultimately a scalar. So this is in fact we should call it a scalar triple product because the output is a scalar, and the way to compute this is a determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. Again, there are two possibilities here. The answer could be 0 or could be non-zero. So whenever this output is 0, then we say that all the three vectors fall on the same plane, or we call them to be coplanar vectors. But whenever the three of them are not in the same plane, then they actually can be used to enclose a parallelepiped whose volume can be determined using this formula. So this actually produces the volume of the parallelepiped, which is generated by these three vectors as coterminous sides. When it comes to the second part, which is called the vector triple product, we have A cross B cross C, and the easiest way to compute this is A dot C into B minus A dot B into C. So you can see that A dot C becomes a coefficient of B and A dot B becomes a coefficient of C. B and C are both vectors, therefore the difference of these two vectors is again a vector. So A cross B cross C is always a vector. Again, it all depends upon how the ABCs are given, whether the output will be a non-zero vector or a zero vector. Okay. Once this is over, we'll now look into what is called the projection of one vector on another, because that is extremely important in understanding what is called the directional derivative in vector differentiation. So let's look into that. So the projection of one vector on another vector. So we can visualize the situation as having a vector A which is being projected onto the vector B. So what you do is you drop perpendiculars from A on B. So these are nothing but the perpendiculars, and this shaded length is called the orthogonal projection of A on B. So we are interested to find this length, and that is easily available from vector algebra as projection of A on B is equal to A dot B by the magnitude of B, or we could also write this as A vector A dot B cap, because this defines the unit vector along B. So we can either use this or you can use that, and mathematically the projection can be positive or negative, as you can easily interpret. Of course, the projection will be 0 only when A becomes perpendicular to B. As I told you, this concept is very important in the context of directional derivatives. I am now going to take you to the vector differentiation, where we will begin with introducing three very important concepts, that namely the gradient, divergence and curl. The calculus of vectors, or what we call vector calculus. Broadly contains differentiation of vectors integration of vectors, or you can also call them vector differentiation and vector integration. Now we have a very important operator, the differential operator del. In fact, we will call it the vector differential operator del, and also put an arrowhead on that. So this will have the features of a differential operator together with vector characteristics. That means ijk's will be also be present. So we define del to be dou by dou x into I plus dou by dou y into j plus dou by dou z into k. There is an operator called the Laplacian operator, denoted by del squared, which is nothing but the dot product of del with itself. So this is del dot del So you take the dot product of this with itself, and you will get dou square by dou x squared plus dou square by dou y squared plus dou square by dou z squared. So we have varieties of laws, theorems based on these operators. And what do we do from here? In fact, it is the vector differential operator del that gives us three possibilities. Obviously, del has got no existence of its own. Similarly, del square does not have an existence of its own unless they are applied on some functions or fields. So now I will take you to the concepts of gradient, divergence and curl.